All right, how's everybody doing? All right, so hopefully y'all had a chance to check out the problem sets and the video helping you out with the solutions. For now, let's move on and take a look at one particular wave, which is sound. Now, sound is a mechanical wave, meaning again that it needs a medium through which to travel. So sound cannot travel through the vacuum of space, right? It needs some sort of material through which to propagate. Now, sound is going to be not just a mechanical wave, but a longitudinal wave, meaning that you're going to have oscillations that occur parallel to the direction of the energy travel itself. Now, sound, in essence, is simply just a pressure wave. And so when we're talking about sound, you've got two different um, portions of the wave, right? You're going to have compressions, which are areas of high pressure within the medium, and you're going to have rarefactions, which are areas of low pressure. So if we were to graph our pressure, right, versus distance, what you would have is this nice sinusoidal wave, right, where your peaks, your crests, correspond with compressions, and your troughs, right, they're going to be associated with your rarefactions, right? So your crests are areas of high pressure, your troughs are areas of low pressure. Now, when we talk about sound, right, keep in mind that, of course, every animal has a different range of different range of hearing, right? Dogs obviously hear frequencies that humans don't, right? Hence the dog whistle. Um, but for humans, right? Humans fall somewhere between 20 hertz and 20 kilohertz, right? So 20 hertz to 20,000 hertz. Now, anything below 20 hertz falls in the category of what we call infrasound, right? So infra, just coming from the Latin for below, right? So below the range of human hearing. Now, certain animals have been known to communicate in infrasound. I'm pretty sure elephants do it to some degree. And then ultrasound would be anything over 20,000 hertz, right? Ultra, again, just meaning above. So infra below, ultra above. Now, obviously, humans, right? That's your ideal range is 20 hertz to 20 kilohertz. But keep in mind, obviously, as time goes on, and depending on how you treat your eardrums, most people are not going to be hearing 20 hertz or 20,000 hertz. You're going to be falling somewhere within that range, right? Because when we're talking about the human eardrum, right, the human eardrum is simply just a very sensitive pressure detector. Um, One interesting thing to note with infrasound, a biology teacher actually pointed this out to me once. Um, think about horror movies. Like, how do they always try to ramp up that tension that you feel before something scary happens, right? There's always these low vibrating notes, right? They're kind of pushing down on the infrasonic range. Well, why do they do that? Well, a lot of your big predatory animals, like big cats, they actually growl in the infrasound range. So it's kind of hardwired into the human biology to sense danger when you approach those infrasonic sounds. So that's kind of interesting, I think, at least. Now, you can Google or YouTube the range of human hearing if you want to hear the 20 hertz to 20,000 hertz. I'd recommend you do that. It's actually fairly interesting. What you'll find is most of our hearing is in that higher pitch range. All right, so let's take a look at a couple of examples. So we want to know what are the wavelengths of sound waves at the limits of human hearing and at the mid-range frequency of 500 hertz. Notes sung by human voices are near 500 hertz, as are notes played by striking keys near the center of a piano keyboard. Now, a couple things to keep in mind, let me pull up my document camera. Control-Shift-2 is when we're working with sound, we're going to typically use, if it's not given to you, let's line this up. We're going to be using sound's speed as 343 meters per second if the problem doesn't give you any other information. Now, sound, just like any other wave, has a speed that's dependent on the medium through which it travels. So, in this case, if we're talking about the speed of sound through air, some problems that I'm going to give you will give you a temperature. Now, the temperature is going to affect how quickly that sound wave propagates. Well, why does that make sense? Think about what we're talking about when we're talking about temperature. Temperature is a measurement of the kinetic energy of particles, right? So if you have a high temperature, right, those particles are vibrating already. Right? And again, keep in mind that sound is a pressure wave. It's a vibration within the air in this case. So if those particles are already vibrating, right, sound is going to propagate faster when the temperature is high. So one equation that's not in the notes that you're going to want is finding the speed of sound at any given temperature. Right? So this equation here gives us our speed of sound with a temperature in degrees Celsius. So 331 meters per second would be the speed of sound at 0 degrees, right? And so if you're given a temperature in degrees Celsius, you multiply that by 0.6, you add 331, you get the speed of sound at that specific temperature. All right, but so let's take a look at that problem here. So we want to know the wavelengths of sound waves at the limits of human hearing and at the mid-range frequency of 500. Well, we're going to use the speed of sound as 343 meters per second. We know the wave equation, right? That the speed is equal to frequency times wavelength. So 343 meters per second is equal to 20 hertz, that's the low end, times wavelength. So go ahead, do the math. 343 divided by 20, and you get a wavelength of 17.15 meters. And you guys are seeing this document camera correctly, right? It's not reversed. All right. So now let's find the wavelength at the higher end of the spectrum. So again, velocity is equal to frequency times wavelength. 343 meters per second is equal to our frequency of 20,000 hertz times your wavelength. Right, and so your wavelength in this case it would be 0.0175. Right, so notice again, the speed is dependent entirely on the medium through which it travels. Right? So as the frequency changes, the frequency doesn't change the speed. It simply changes the wavelength. So at low frequencies, you have a very large wavelength, and at high frequencies, you have a very small wavelength. All right, so again, avoid falling for that trap that frequency and speed are related, right? Speed is entirely dependent on the medium itself. Now, the last portion asks us to find the wavelength at 500 hertz. So again, go to our wave equation, where the speed of sound is 343 meters per second, 500 hertz times your wavelength. So 343 divided by 500, and you get a wavelength of 0.686 meters. But again, the key thing here with this example is recognizing that the speed remains independent of your frequency, right? The frequency only will affect your wavelength, right? Again, high frequency, low wavelength, low frequency, high wavelength. So let's take a look at another example. So right when you're trying to see a fetus, right, use ultrasonic waves. So to make a sufficiently detailed ultrasound image of a fetus in its mother's uterus, a physician has decided that a wavelength of 0.5 millimeters is needed. We want to know what frequency is required. So again, let me pull that question up real quick. All right, so we're given a wavelength of 0.5 millimeters. We are given also that the speed of ultrasound in the human body is 1,540 meters per second. Right, notice that when we're talking about the speed of sound, the speed of sound, when you're looking at the types of materials it travels through, right, the speed in gas is going to be less than the speed in liquid is going to be less than the speed in solid. Right, so when we're talking about the human body, it travels at 1,540 meters per second, significantly faster than it does through air. So let's go ahead and list our knowns and unknowns here. We got our speed of 1,540 meters per second. We got our wavelength of 0.5 millimeters. Again, make sure that you're always working in meters. So that's 5 times 10 to the negative fourth meters. And so if we want to know the frequency associated with that wavelength, again, you just go back to the wave equation. That's the nice thing about sound is this is one of the most important equations there. So 1,540 meters per second is equal to your frequency times 5 times 10 to the negative 4 meters. So you get 3.08 times 10 to the 6 hertz. So again, a very low wavelength indicates a high frequency. We okay with that example? Again, if you got any questions, jump into the chat and let me know. All right, let me pull off the webcam. There we go. All right, now, before we jump into specifics of sound, there's some things that are worth considering when we talk about sound. Now, we said that your go-to speed of sound in air is 343 meters per second, right? And that's pretty fast, right? But I want you to consider this. Light travels at 3 times 10 to the 8th meters per second, right? So sound travels at 343 meters every single second, whereas light travels 300 million meters every single second. So there's a big discrepancy between the speed of sound and the speed of light. Comparatively speaking, the speed of sound is very, very slow. Now, you guys have used that difference between the speed of light and the speed of sound in your lives at some point, I'm willing to bet. Now, think back to when you're a kid and there's a storm coming. Right? Your folks always told you, if you see the lightning flash and then you count until you hear the thunder, that'll give you a relative idea of how far away the storm is. Right? And that's actually pretty good physics that they were teaching you there. Unfortunately, the distance that they gave you was generally wrong. Right? Typically, they would tell you that it was a mile away, right, for every second. So let's take a look at what that looks like in terms of physics. So for all intents and purposes, right, once you see that lightning strike, light travels so fast that we can just assume that it hits you pretty much instantaneously, right? The amount of time that it takes for the flash of lightning to reach your eyes is so minuscule that it doesn't matter. So let's say that you see a lightning strike and hear the thunder 1 second later. Right, and we want to know how far away the storm is. Well, let's say it's ideal conditions, meaning that your speed of sound is 343 meters per second. Let's find out how far away the storm is. Now, again, sound is a wave. It travels at a constant velocity as long as the medium through which it travels doesn't change. So 343 meters per second is equal to distance over 1 second. So it means it's 343 meters away from you. Right, so it's roughly a third of a kilometer away for every meter. So if we were to convert that into miles per hour, or sorry, miles, so 343 meters, there's 1609 meters in 1 mile. You get roughly 0.21 miles, right? So for every second that elapses between seeing the lightning strike and hearing it, about 0.21 miles is traveled. So there you go. You can use that when the next storm hits. Now, the reason I bring that up is because it's always interesting when we talk about sound to think about, common misconceptions we have about, sound and light and their relative speeds to each other. So, take for instance every action movie or action TV show that you see. Right, your hero, he sees a big explosion, and what happens? Well, he hears the explosion at the same time. Well, typically speaking, if there's a big old explosion and you see it and you hear it at the same time, what's probably true? Well, you're probably not among the living anymore, right? You generally don't want to see and hear a big explosion at the same time. So that's one thing, right, that your big action movies always get wrong. So, for instance, here's a really good example. We've got ourselves here a video of a test explosion out in the desert. Now, I want you, as we look at this, to notice the time delay between seeing the explosion and actually hearing it. right? So there's a significant delay between seeing it and hearing it. Now, here's an interesting question also. Can you see a sound wave? Well, a sound wave is simply a pressure wave, right? So I want you to look at this video again, and you'll actually be able to see the sound wave, right? You'll see the sound wave propagating in the dust that's generated by this explosion. But also, right before you hear it, you're going to see a shadow right about here in the video sweeping over the ground. That shadow that you see is the shadow of the pressure wave. And right when it hits the camera, that's when you're going to hear the sound. Right? So, right here, you see the sound wave. And again, look down here for the shadow. A little further back. Right there, you saw that little shadow come, hit the camera. Boom, you have sound. Right? So technically, what you're seeing there is the shadow of the sound wave. Now, you can also see this really well in something like a volcanic eruption. So I believe this is it. Yes. Now, what I want you to do with this video is watch the clouds. Right now, obviously, you don't want to be close enough to a volcanic eruption to where you see it happen and you hear it happen at the same time, because again, that generally means that you're in a bad situation. So notice, right, the clouds and what you see there. So again, let's watch that once more. Again, notice, significant delay between seeing it and hearing it, which means you're safe. But again, look at those clouds. You see that shock wave, that pressure wave, that sound wave propagating from the center of the disturbance, right? The source of energy, that volcanic eruption, right? And once that shock wave reaches the boat, then you hear it. Right, so see those clouds up there? So there you go. One other cool thing that we can look at, this will be the last thing for today. Um, Russian rocket explosion, yes. Is with this video, the weird thing I want you to think about is what you're hearing versus what you're seeing. Right? So this is going to be a Russian rocket taking off. It's going to end up going haywire. It's going to explode and it's going to fall to the ground. Now, it's going to start taking off before you even hear the sound of its engine starting up. Right? It's going to turn into a fireball, and you're still going to hear the engines firing. and then it's going to already be exploded on the ground before you even hear the explosion. So what you're hearing is time delayed versus what you see. There's like about a 6 to 8 second gap between what your visual input is and what your audio input is. So really think about what you're seeing here versus what you're seeing versus what you're hearing. All right, so again, you see the rocket taking off before you even hear it. You see the rocket burst into flames and you're still hearing the rocket's engines. And then when there's that explosion on the ground, you hear silence as that rocket's free falling to the ground, and then you hear the rocket itself. So, those are all kind of interesting, applications of sound versus light speed. So, those are just a couple cool things to, think about. So that's where we're going to stop off for today. I don't want to jump into energy and intensity for now. I'm sure you guys got that email from the College Board about taking the exam online. Um, you know, you do what you think you need to do. I honestly do not blame anyone who wants a refund. I mean, because that's not ideal scenario. From what I've seen, it's going to be only free response. And it's going to be free response to the level that you can't Google anything or, um, you know, use Snapchat to help each other out. So I'm not going to lie, it's probably going to be real tough. So kind of think about what is best for you. Um, and again, I don't blame anyone who is thinking, maybe they should back out. But if you want to keep going, that's great. Um, and we'll keep moving through this unit because I have a feeling that this unit will still be on the free response. Um, but yeah, again, office hours are on Zoom Tuesdays, Thursdays, 2 to 3. If you got any questions, let me know. Have a good one.